Hi everyone, this is Shayan. Welcome back to another video on Olympiad geometry. Today we're going to look at not one, not two, but three amazing problems that are kind of going to use the same trick, and I'm going to show you the trick in a bit. But first, of course, try the problem on your own. So make the diagram, give it a shot. Assuming you've done that, I'm now going to show the diagram. So this here, we have omega, which is this circle. So this circle is omega, and we have a point, we have an acute triangle ABC, and a point inside that triangle X, such that BAX, so this angle right here, BAX, is 2 times this angle XBA. So it helps to like maybe denote them by something. So if this is alpha, so XBA or BAX, if XBA is alpha, then BAX would be 2 alpha. Similarly, if I have XCA or ACX as beta, then XAC will be 2 beta. So that's a unique point inside this triangle. And then M is the midpoint of the arc BC, essentially. So the arc, the part of the arc containing A. So it's this midpoint right here. So we need to prove that XM is equal to XA. And now you can try doing this, and maybe you can figure out a different way. But the one I'm going to show uses a somewhat different construction. So it's like a magical construction that'll almost make this, like, it'll make this very easy. So, and it's not that hard to think of. I mean, you can whenever there's this weird angle conditions, you can maybe think of drawing something, a line or something that will bring in more angles, maybe some isosceles triangles. So I'm gonna go ahead and actually just show you what I mean. So essentially, you need to make this. So let me just make in the angles in this one as well. So this is alpha, this is 2 alpha, this is 2 beta, this is beta. So we make XP, so I'm going to write here, let P and Q be such that, so number one thing is that XA is equal to XP. So XA is equal to XP, which is also equal to XQ. So that's the definition. We make 2 isosceles triangles here. And now we're going to investigate what happens to the angles. So obviously this angle here will be also a 2 alpha. So now angle XPA, this is a P, is a 2 alpha. And also angle XQA is 2 beta. But there's also another thing that we can get from here. Maybe try and pause and find some other angle that we can find from here. And it's this angle. So PXB. This will also be alpha. Why? Because the external angle for this triangle PBX, the angle APX is 2 alpha. But we know that the exterior angle is the sum of the two opposite interior angles in any triangle. So essentially PBX plus PXB has to equal 2 alpha. But we know PBX is alpha. So this automatically implies that PXB is alpha, and on the other side QXC is beta. So this is 2 beta and this is beta. So QXC is beta. But this tells us something more. This tells us, because this is now another isosceles triangle. So PX is now also equal to PB. So in this list of equal things, I can now add. So I know that XA is equal to XP is equal to P is equal to XQ, which is also equal to BP and CQ. So these are a lot of equivalents that we now have. And so now think about it. We need to show that XA is equal to XM. But we know that XA is equal to so many other lengths. We know it's equal to XP, which is equal to XQ. So first focus on maybe these two only. So XP and XQ. So what can we show that will automatically solve the problem? At this point, we know that XA is equal to XP is equal to XQ. So this implies that X is the circumcenter of triangle APQ. So if we want to show that XA is equal to XM, that will automatically imply that all of these 4 points, the points A, P, Q, and M, lie on a circle. So that's what we want to show now, that A, P, Q, and M are on a circle. But it turns out there's actually a lemma on this that will, that's a very important lemma. So that lemma is exactly what we need to show. So I'm going to scroll down and bring you to the lemma, and you can maybe pause the video and try to prove it. So the lemma says that if you have any triangle ABC, so this is there's two parts. One is the forward one, and then there's the converse of that. So the forward one says that if you have any triangle ABC and you have the mid arc of BAC, so BAC, the one containing A, if you have the midpoint of the arc, and you have 2 points X and Y arbitrary on AB and AC respectively, then the lemma says that if BX is equal to CY, so if these two lengths are equal, then AX, Y, and M, it turns out that they're on a circle. Surprisingly, they are indeed on a circle. And the converse of this would be obviously that if you have a circle containing the points M and A that passes the lines AB and AC at points X and Y, then BX would be equal to CY. So these are both like the converses of each other. So maybe pause the video and try to prove that it's basic angle chasing here. And once you're done, maybe I can show it and you can compare your result. So just use this diagram, maybe make a few other lines. I'm going to scroll down. I have the proof written down already just to save some time, and obviously because it's neater writing earlier. So the first part in the proof is you draw the lines MB and MC. Now this automatically means that MC is equal to MB because M is the midpoint of the arc, and that's what the definition of the midpoint of an arc is, that MB is equal to MC. And then notice that XBM, these yellow angles, they're both equal. Why? Because XBM is essentially ABM, and the other angle, which is YCM, that's just ACM. So we know that ABM is equal to ACM, and so that's why these two angles are equal, because they're made by the same chord AM. So we have one pair of sides that's equal, which is MB and MC, and by the definition we know, so this is, we're trying to prove the first part here. So we know that BX is equal to CY. We're trying to prove that AX, Y, and M are concyclic. So because we know that BY is equal to CY, so all of these three things combine, this one, this, and the third one, we have two sides and an angle between them. So for this triangle, for these two triangles, XBM and YCM, we have two sides and a pair of angles between and an angle between those two sides. So this automatically implies that these two triangles are congruent. So right here we have these two triangles congruent. But this means that the angle XMB is equal to the angle YMC. So these angles I marked in red here. So these two red angles are now equal. So we need to show that XAMY is concyclic. So if we can show that XAY is equal to XMY, we're done, right? Because angle made by the same segment should be equal. angles in the same segment, if they're equal, then this means that it is they lie on a circle. So let's look at angle XAY. Well, XAY is equal to BAC because XAY, BAC, they're just the same angle. This angle is equal to angle BMC. So once again, by they're both made by the same chord BC in the same circle. So XBAC is equal to BMC, and so the angle BMC is the sum of the green angle right here, which is the angle BMY, and so it's equal to the green angle plus the red angle, right? Because this is the one angle and then this is the other. So if you add them, you get the angle BMC, which is essentially XAY. But notice that angle XMY is also the sum of red plus green. This is the red angle, that's the green angle. And so I just marked them this way to show you visually how this works. So because they are both green plus red, both these angles are the same. So this means that XAMY is concyclic. And so we have shown what we needed to show in the first problem in our video. So we now know that we can now, if you were to write the proper proof, you would now quote that lemma, and you would maybe even give the proof for that, and then you can just say that by the lemma below, I'm going to write below because I wrote it below, but we can just say that by the lemma below, we know that since in triangle ABC, PB is equal to QC, we know that A, M, P, and Q, they are cyclic. So AM, PQ is cyclic, and this means that XA is also equal to XM, and we are done. So this was a beautiful and short proof for this question. So now we're going to see another problem that uses the same thing, and I encourage you to try that one on your own. So let me scroll down. This is the second problem. So we have a problem here. Please pause the video, try this on your own. Let me now show the diagram for this. So essentially we have N as the midpoint of the arc ABC, so that's an indicator that we could use that lemma. So this lemma is on the midpoint of the arc ABC. It's essentially the arc, the midpoint opposite on the same side as like the third point in the triangle. So whenever you see this point, this midpoint in any problem in a contest, maybe you can try and think of this lemma and see if you can use this. So remember, this midpoint is on the same side as the third point in the triangle. So in any triangle, if you see this midpoint, you can maybe think of that stuff. So let's try and understand the rest of the diagram. So we have N as the midpoint of the arc ABC. So it's the chord AC, the midpoint, the perpendicular bisector of this chord passes through N. And then from that midpoint in this triangle, we draw two tangents to the in circle. So with this in circle here, we draw the two tangents. It meets the in circle at the point P and the point T. Then we take the point B and we join it to the point P, and then we let the BP, we extend BP to meet the main circle again at P1. And similarly, we extend BT and let it meet the main circle at T1. And so now we have the diagram. So in any problem, you would always make an accurate diagram and then try to notice some claims from the diagram. So we already know that we have to use that lemma in some way. But before we can do that, there's one claim that we need to prove. So maybe look at the diagram and try and find a claim and try to prove it. So assuming you've given it a go, I'm now going to share. So looking at the diagram, we could see that the line P1, T1 kind of looks parallel to the line AC. And so how can we go about proving it? It's actually, if you're an experienced problem solver, you would probably notice this right away. But because IP here is equal to IT, so remember, I is the in center. So because IP is equal to IT, there's something known as isogonal conjugates. So you can say right away that because IP, so in my proof I can say that, let me change the color for this problem. Let's say that in my proof I can say that because IP is equal to IT, this implies that essentially P and T are isogonal. Now what does this mean if you do not know this? Essentially, isogonal means that these two isogonal conjugates are points that are essentially, they lie on the reflection of the angle bisector of, essentially, if you, for example, if I have the line BP, then what this means is that the line BP is a reflection in the angle bisector of the line BT, meaning that this angle is equal to this angle. And the reason, if you know what isogonal conjugates are, the reason this makes sense is because if IP is equal to IT, this means that P and T are bisymmetry. They have the same angle here. In fact, if we just forget about this isogonal conjugates, and let's say you don't know what they are, you can still prove this using basic angle chasing. So notice that because the BI is the angle bisector, we know that the angle ABI is equal to angle CBI. But we also know that because angle IBP, oh, actually, I think we're going to need something else here. We should probably prove some other claim first. Let me just pause the video for 1 second, and I'm going to return. There's one thing that I am being iffy about. Wait, just 1 second. Alright, so I'm back. So sorry. So it turns out there is a thing where IP is equal to IT directly implies that P1 T1 is parallel to AC, because then P1N would be equal to T1N, but we're not going to show that first because that's going to be a little complicated. So what we're going to do is we're going to think of the problem in reverse. We already know that this has to be true because from our diagram as well, and because it can support another claim, because if this is true, then we would know that essentially P1T will have the same midpoint of the arc. So because P1T1 also has N as the midpoint of the arc, we can almost be done, because remember, if this is true that N is the midpoint of this arc, of this chord, and then if we focus on the triangle P1BT1, we want to show that PP1 is equal to TT1. But if that is true, if P1P is equal to TT1, then that would automatically imply that P1B, T, P, B, and N are concyclic by the lemma that we just did. So if we can show that N, B, P, and T are concyclic, then that would complete the proof. So let's start by trying to prove that, and then move our way backwards and prove P1 T1 is parallel to AC, and then that would pretty much complete the proof. So maybe pause the video and try and do that. So let's begin the proof. First of all, we notice that I, P, N, and T are cyclic, because that's pretty obvious that angle I, P, N is equal to angle I, Tn is equal to 90 degrees. This is obvious because they are both tangents. And then this means that if I can show that angle IBN is also equal to 90 degrees, that will show that indeed B is also on that circle, and that would be very helpful for our proof. So if we can show that IBN is 90, then we are almost halfway done. But it turns out that that's also pretty obvious if you remember the fact that we've done in a previous video. So remember about this midpoint, the midpoint of AC, essentially the midpoint of the one of the chords in a triangle that's on the same side as the third point. So this midpoint has a property. We did it in the previous video, that for example, if I have any ABC triangle here, so trying my best to not mess it up. So if I have ABC and the midpoint of this arc right here, so we learned that AM is the angle bisector. You can check out my first video, which was on the IMO 2021 problem. We learned that AM is the angle bisector is the external angle bisector. My handwriting gets worse as we proceed, so I'm going to try to make it better now. So is the angle bisector of angle BAC, and it's a pretty simple angle chase actually. Let me even show that to you in just 1 second, because we've actually done this before. So if anyone wants to try it, they can do that on their own. So this is M and this angle. So if we make MB and MC here, this is A, this is B, this is C. So first of all, we know that MBC is equal to MCB, right? But notice, oh, actually that's what we want to show. So we want to show that MBC is equal to MCB. So we're making the external bisector, and we want to show that MB is equal to MC. So essentially this angle is equal to this angle. So we start with this angle right here. Let's call a point E on this line. This is getting really messy here. I'm going to try my best to explain. So let me extend this line. Let me choose a point on this line. Let's call that E for now. So remember, if angle EAM is equal to angle MAB by the definition of the external angle bisector. So this angle, if this is alpha, then this is equal to angle MBC. So EAM is equal to MBC, which is equal to alpha because of the cyclic quadrilateral, because it's the exterior angle. So essentially EAM is 180 minus MAC, which is 180 minus MBC. So EAM is equal to MBC is equal to alpha. And then notice that MAB is also alpha by the definition of the exterior angle bisector. So MAB is equal to MAC by the angle in the same segment. That's also alpha. So starting from the fact that it's the exterior angle bisector, we prove that M was the point where the exterior angle bisector crossed the circle. We show that M is indeed the midpoint of the arc. So using this lemma, we know that the angle in our diagram, we now know that this angle CBN, so let me write, this is angle AN in our diagram. Oh, let me actually, this is part of that proof, let me remove it. So this video is going to get a little longer than I wanted it to, but that's okay. So angle CBN is equal to, I claim it's 90 minus B over 2. So remember this fact, if you have an exterior angle bisector and it cuts the point M somewhere here, then the angle M, if this was the diagram, then angle MAB will always be this angle. If this angle is alpha, then angle MAB will be 90 minus alpha over 2. And this is simple because it's the exterior angle bisector. So this angle is equal to this angle. So both these angles are equal. So this is alpha, this is alpha. but both of these angles, the sum of them is 180 minus the angle B here. This is angle B, not some beta. So this is angle B. We know that 2 alpha is equal to 180 minus B, so alpha itself is equal to 90 minus B over 2. So this is 90 minus B over 2, but IBC is equal to angle B over 2, right? Because it's the by definition, it's the angle bisector of the angle B. So the sum of these two, which is angle IBN, is now 90 minus B over 2 plus a B over 2, which is equal to 90 degrees. And so we have shown that IP, BN, and T is cyclic. So this part is done. Now we're almost done. We can use this fact to show that indeed P1, T1 is parallel to AC, or that N is also the midpoint of the arc P1, T1. And that's pretty easy. We can show that angle, now that we know that these are cyclic, we can say, let me make sure that this is point P. So angle IBT, let's see if you can follow this. So angle IBT is equal to angle IBP. And the reason is that because IB is equal to IT by symmetry, it's a kite, there are two equal tangents, so it's a kite. So because they are equal chords, they subtend equal angles. So equal chords make same angle. And so because of this, we know that this angle is equal to this angle. But let me choose another color. So we know that these two orange angles are equal, but we also know that these two red angles are equal. So we know that angles ABI is equal to angle CBI, and we also know that now angle P1BI, which is the same as angle PBI, is equal to angle T1BI. T1BI. So the difference of these two angles will also be equal. So this means that angle CBT1 is equal to angle ABP1. And this is very important. This is almost the last step, because this implies that the angle made by the chords A1, P1 is equal to the angle made by the chords C1, T1. But this means that these chords have to be the same. If their lengths have to be the same if their angles are the same. So essentially, we know that because this is an isosceles trapezoid now, P1, T1 has to be parallel to AC. And because of this, N is the mid arc of P1, T1. And at this point, you can just write that by the lemma earlier, we are done. And the reason, because if you focus on the triangle P1, B, T1, we have shown that B, N, T, and P are cyclic. So because B, N, T, and P are cyclic, T1T has to be equal to P1P by the lemma. So at this point, you can just write that P1P is equal to T1. You can obviously, if you were doing this problem on a contest, you would write down the lemma again and the proof for that, and then you would say that this is equal to this by the lemma above or below. Yeah, lemma above. And we are done. And so this is already a long video, but maybe we can just squeeze in one more problem. So this problem is on the same lemma, so go ahead and try this one completely on your own. So let me just show you the diagram for this one. This is right here. Oh no, here. So we have, and this actually has a kind of a huge hint, so you might want to try it. If you want to try it on your own, do not look at this. So we have K and L are 2 points on the arcs AB and BC. So we have a triangle ABC here. And on these arcs, so arc AB and arc BC, we have 2 points such that KL is parallel to AC. So essentially it's just KL is parallel to AC. So this is true. We have an isosceles trapezoid here. So show that the incenters of ABK and CBL are equidistant from the midpoint of the arc AC, containing the point B of the circumcircle of ABC. So the major hint for this problem is to let here X is the incenter of ABK. So I just constructed that, and then Y is the incenter of CBL. So I have the incenters. The key idea here was to extend the BX and let it meet the circle at a point. Let's call that P, and let Y meet it at another point here, which is Q. So now once again, try and think about making this look like the configuration that we've just done. And we already have the M and the B. So the two candidates for the other 2 points, they could be X and Y, right? And that would mean, if we're thinking in reverse, that would mean that PX is equal to CQ. So if we can show that, then that would pretty much show that indeed X and Y are those 2 points, and that indeed X, M, B, and Y are cyclic. If we can show that PX is equal to CQ. But notice that's actually pretty obvious, because for one thing, P and Q, because they are the extensions of the angle bisectors of these two angles, essentially PQ has to be also parallel to both these lines. And the reason is obviously because these are the midpoints of the arc. So P is the midpoint of the arc AK, and Q is the midpoint of the arc CL. And this is a very basic property of midpoints and mid-arcs, that if you join the two, it's going to be parallel. So because it's parallel, this essentially, at this point, you can use the in-center x-center lemma. And so I can write in my proof. So I can start by saying that by the in-center x-center lemma, Px is equal to Ax. Sorry, Px is equal to, notice that we know that P is the center of a circle passing through K, X, and A. If you don't know what the in-center x and lemma is, maybe search it up. But essentially, this is that same triangle, that same circle with the radius PK is equal to PA is equal to PX. So all these three lengths are equal. So PX is equal to PK is equal to PA. But notice that we know, because PQ is parallel, we know that, and this is going to be an isosceles trapezoid. So AP, this last length, is actually equal to CQ, right? Because of this isosceles trapezoid thing. But notice that we have the same thing on the other side. CQ, Q is the center of a circle that passes through C, Y, and L. So CQ Q is equal to CL, which is also equal to CY. So we have shown that PX is equal to CY. So CQ, that's the important one. So PX is equal to YQ is the important one. This is not CY, this is QY. So PX is equal to QY is the important one. We have shown that because PX is equal to QY, now by the lemma above, once again, we can now say that MBXY con cyclic. They are on a circle. They lie on a circle. There will be a circle that these four lie on. And at this point, it's just angle chasing to show that indeed what we need to show is that the incenters are equidistant from the midpoint. So we need to show that mx is equal to my. So try and chase some angles and finish this up. So let's start by finding angle mxy. Once again, remember, keep the lemmas in mind that we just did. So angle mxy, if we can show that's equal to myx, we're done, right? So let me first try to express mxy in terms of any other angles that I know. So I know this is 180 minus angle mby, because these are now on a circle. So 180 minus angle mby. So, but mby, I actually kind of know how to represent this, because notice that mby or mba is once again, this is 180 minus angle mba plus angle aby, right? Or I can actually say abc plus cby. But you'll see in a minute why we're doing this. So what do we know about mba? Well, this is the same angle from the previous question. This is equal to 90 minus b over 2. We just did that. We saw why that if mb is essentially the external angle bisector of this angle, this ABC. So we know that mba is equal to 90 minus angle b over 2. And angle ABC is just angle B. So we have angle MBA, angle ABC, and finally angle CBY. So I'm just going to call CBY X for now, okay? Just for, because we know that this X is also equal to the angle which is, well, because this is the angle bisector, this angle is also X. And is there any other angle that we know is also X? So yeah, we do, because these are the same chords. These are the same length, because this is essentially now is when we use the fact that KL is parallel to AC. Because KL is parallel to AC, we know that all these angles, this angle is X, so we know that essentially KBA is equal to CBL, because these are both the angles made by CL and AK, and CL and AK are the same. So essentially this angle is X, this is X, this is X, and this is X. So wherever now I see an angle that's X, I'm just going to write X instead of it. So this is X now. So now let me make this look a little better. So first of all, this B minus a B over 2, that's just a plus B over 2. So a 90 plus B over 2 plus an X, and then when I subtract a 180 from it, I get, well, 180 minus 90 is just a 90, and then this negative will come as it is. So 90 minus B over 2 plus an X. Remember, we're looking at angle MXY right now. So let me scroll down. And now let's look at angle MYX. But angle MYX is equal to angle MBX. But angle MBX, well, that's just equal to angle MBA minus angle M, or angle I should say XBA. So it's this angle removed from the total angle. So from angle MBA, if you remove the small x, you get the angle MBX. But we know what angle MBA is. We know that's just a 90 minus, actually there should be a negative here, sorry for that, 180 minus, we're subtracting, so this negative will also make this plus a negative. So 90 minus angle B over 2 minus, well, what's XBA? That's just an X. So right here we have just shown that these two angles are the same. Angle MYX is equal to angle MXY, and we are done because that implies that MY is equal to MX. So sorry for making the video so long. I hope to see you in the next one. Thank you so much for making it to this part.